So, how I'm using earbuds today, if that's what these things are called. Does it sound better?
Sounds pretty good.
Yeah.
Does it sound the same or a little better than without using them?
Pretty much same, better.
Same. Okay.
Yeah, pretty much.
Okay. I ordered a headset. Carl just got one and he said sounds better than his old one. So I ordered a headset. It's supposed to come by next week. So actually maybe today. I'll have it for Tuesday's class. So that's that. I'm also going to start out with the document camera just because on Tuesday we did that problem using the document camera. So I want to start out using the document camera just because I want to highlight what we did already and I have the work on a sheet of paper. So we'll start out using the document camera, then I'm going to turn to OneNote and see how it goes and see if I get booted out a few times, and we'll see. And so we did a 2D statics of particles problem on Tuesday. And today we're going to do another 2D problem and we're going to do a 3D problem. And while I'm doing these problems, I'm introducing some new concepts to you. So we're going to do the 2D. And then when we get to the 3D problem, I'm going to have you go into breakout rooms to work on it. And then I'll bring everybody back together. All right, so to start out, I just want to share the screen just to show you where we are. So I'm in modules on our Engineering 35 page, and I am in the student view. So this is exactly what you see. So remember, the first module is understanding Canvas, and I'm not getting many Canvas questions anymore. So either you know it all, or the CTC is doing a great job, and I imagine it's probably a combination of both. Then in the summer, we did components. So the first topic we did in statics was finding components, 2D and 3D problems, angles and ratio problems using our 3-step process, and doing 3 checks along the way. And then here was just an overview. Then the next topic that we did after components was resultants. And we did resultants by summing up, doing it all vectorially. And then the third topic we did was setting up the problems, 2 and 3D statics problems. And now the fourth topic is actually doing the statics of particles problems. Okay, so we're finishing up is it the second week of class or third week of class? So I don't know if it seems like we're going quick or slow. I'm not sure how it is, what your perception is, but we had components. Everybody should be totally comfortable with components. Everyone should be totally comfortable with resultants. Setup, you should be very comfortable with. In fact, this coming Tuesday, we're going to have another quiz, and it's going to be a setup quiz. And I set it up like Jordan said, where I just open it at a certain time and then close it. So it's already posted and it's in the calendar. And now today we're going to finish up statics of particles. Tomorrow in the lab, you're going to be working on pulleys, which I'm going to introduce a little today. And you're going to be working on it a lot tomorrow. And then you have an online quiz in pulleys. And next week on Tuesday, we're starting to calculate moments using right-hand rule, torques from physics. So I'm going to stop sharing now. And I'm going to use the document camera. Okay, so everybody see what we're looking at? I'll press the focus. Okay, remember setup, just a reminder in setup. You take a look at the schematic that's given, you look at the words here, and names. I'm gonna start from the bottom because I'm always starting from the top and poor Adam's getting called on all the time. So I'm gonna start from Victoria. Victoria, you're here, I see you. So we look at the schematic, we look at the words, and in setup, what's the first thing we're doing? What do we write?
Our given.
Right, our given and our find. Great. Okay, Tony, after we do the given and find, what's the next thing we do? Okay, Tim, I'm gonna go to you. After given and find, what's the next thing we do?
The forces table.
The table. And after the table, we could determine how many unknowns there are, which means how many equations, and then we know how many bodies to solve, to do free body diagrams of. And then Peter, after the table, what's the next thing we do? Peter, can you hear me?
Sorry, I forgot to unmute my mic.
Okay.
And we need to determine how many equations we need based on
Correct.
the
And
number
then,
of magnitudes. Determine how many bodies we need to put for our
Right.
body diagrams.
and then free body diagrams. So, right, so the setup includes given and find, table, free body diagram. Okay, and that's what we did last week. And then on Tuesday, we went on for this problem. We knew what the weight is. We did a sketch here. We saw, okay, here's a weight, here's a tension. And we noticed that there's this force right here, which we wound up calling a strut. And we put the strut direction in this direction. Okay? And then Miles. What was the next thing we did, which I'm showing you here? This is what we had. We had our free body diagram, and from our free body diagram, what did we set up?
The components?
Right. We solved for the components and we did our check. And then we solved for the components of basically all the forces. So we had the tension, we had the strut, and we had the weight. And we found the components of all those forces in terms of the magnitude of the forces and using the unit vector. In terms of the weight, we had the value, so we had the value in here. And the reason for doing that, this is really important, you guys. I know in physics, you jump straight to the equilibrium diagrams. In engineering, we don't do that because our problems are really complicated and we want to go and check things as we go along. So if we screw up at the beginning, we see that we messed up. We don't want to get all the way to the end of the problem and then find that we messed up. So we solve for the components of the forces first, and we do the checks first. So in this case, we have a plus or minus visual check, and we have the unit vector check. So we do the checks first before we do the equilibrium diagrams. And let me add, the last quiz that you did in setup, there were people, there are probably about 10 of you, 5 to 10 of you, who wrote positive, negative, visual check, okay, but your negatives and positives were wrong. Did you hear me?
They weren't. Okay.
5 to 10 of you said you did the positive and negative check, but you had the wrong signs here. Remember what I mean by the positive and negative. Let's look at S. S has a negative X. Look at the picture. Yes, X is going into the negative direction for X. S has a negative Y. I look at the picture, the free body diagram. Yes, S goes in the negative. Now I could do yes plus or minus visual check. Same thing for the tension. I got a negative in the X. Yes, T1 is in the negative direction for the X. For the Y, it's in the positive. So from now on, only write the positive or negative visual check being okay if you actually checked it, because now I'm going to start taking off more points. The reason for checking it is just that, to check your signs before you move on. Because if your signs are wrong here, your answers are going to be totally wrong at the bottom. And I'm not going to ream you for wrong answers at the bottom, but I am going to check as you go along, because I want to make sure that you're catching your mistakes before you get to the end. Okay? Okay, once you do the components, then you set up your equilibrium equations. Sum of the forces in the X, you add in Tx and Sx, and it equals 0. And this is my equation 1. I always box it in. And then I did sum of the forces in the Y, and there was a T1Y, and there was a S, and then there was a minus 1,000 equals 0. Remember, sum of the forces in the y and x always have to equal to 0. And then this translated to my equation 2, where I put only the variables on the left side and I have my magnitude on the right. And then using my calculator, I solve for what T1 and S1 and S were. And Myra, can you tell me when I got a negative S, what did that mean?
That's the way the arrow should go.
Okay, so explain that better for me. I don't
So-
understand what you mean.
So it's supposed to go the other way.
Great, that's what I want to hear. So on the free body diagram, you assume a direction, and you could assume any direction. When you get a negative, it means that the direction you chose, it's going in the other direction. It's not a bad thing. You're going to see when we get halfway through statics, you're going to get negatives tons because we don't always know where the direction is in the connections of beams and things. So what I highlighted here in kind of like a peach color or green, your answer to this problem is your free body diagram and your answers. They go hand in hand. You got a negative here, so the reader knows that S actually goes the other way, but you leave it drawn the way you have it. Okay, any questions? I'll look at the chat.
Joanne, I'm not sure if I missed a video or something, but at the end of this problem, you just said, plug it into your calculator and this is what we get. But I'm not
Right,
sure
we
we went
didn't-
over that method.
We didn't go over that yet.
Okay.
Yeah, I just want to recap what we did last week before I move on.
Okay, thanks.
To expand on that, do you want us to actually show the work for finding T1 and S, or can we just say like matrix magic and then just write
Magic.
the answer?
Great, great.
Yeah.
Okay, I'm assuming from the questions being, I'm assuming everybody's cool with this. So now let's go to the other thing. That's all you have to do is, as long as you're showing me the two equations, you could just write calculator and show me the magic answers. Okay, and there are two ways in the calculator. Well, certainly mathematically, how can I solve this? You guys know this from algebra. You isolate one variable, you shove it into this equation, you solve for S, then you go back in here and find T. Okay, so you could do it mathematical if you want. Two equations, two unknowns. But the other two ways of setting it up using the calculator is, the calculator has a method for you could plug in two equations into your calculator and two unknowns, and then you hit a button and the calculator gives you the answers. Otherwise, you could set it up as a matrix, and the matrix is A times B is equal to C. And we know A because we know the coefficients of T and S, and we know C because we know the 0 and the 1000, and we solve for B. My plan today is to make a short 5-minute video on how to set up the matrices. And then I want you guys, I'm going to give you a workshop where you guys can work together on figuring out who has the same calculators and figuring out how to do it on the calculator. But I'll show you how to do it on a generic calculator, okay? So today, one thing for me is I'm going to make a video on solving systems of equations with the calculator. And I'll also create a worksheet that can be a group worksheet where you're having the same calculators, and then you'll submit it. You'll hand it in by a submission. Okay?
Joanne,
So
you asked
it's-
me to remind you about something about posting the solutions.
Oh, yeah, thanks. Thanks. Daniel, change your name to Isaac. So I know as a student, after I did my homework, I always really liked to check the answers. I like to check the process, not just check the numerical value. and then I got confirmation as to whether I did it right or not. Now, I can post the solutions if you'd like, if that's helpful. The thing that scares me though, is that if my solutions are posted, you may not use grit and work hard on, let me look at you while I'm talking about this. If I post the solutions, I'm afraid that people won't work their ass off to try to do the problem first and then compare it. But it's really up to you on what you wind up doing. It's just that this is, like I said to you, this is the most important class that you take if you're a civil, architectural, mechanical, aero, industrial, marine. So you want to leave this with really good knowledge. But I think, so I want to get your input on this.
Yeah, I mean, certainly we have to be self-motivated in that regard to get the most out of the class. And I would also add that, you know, having access to the solutions doesn't mean that we have the process written down in the way that's going to get us that full credit.
Well, the solutions, those of you that have the solutions manual, they're solving some of the problems the physics way. I don't know if you know, a professor writes a textbook, a graduate student does the answers. So the graduate student answered the questions a lot with parallelogram rule. And I want you to do the steps that an engineer has. So I think I'm going to post I'm going to post my solutions so that you could check your work, okay? Is everybody good? Okay, Colin, you have to tell us what's so funny, because I think you're watching something that's kind of cool and I think you should share it with us.
Oh, what do we got?
Sorry.
What?
Sorry.
Oh, okay. So it's not, okay. Something to share. Okay. All right. So, so I'm going to post the solution so that you can check your work and then determine whether you did it correct or not. And then when you submit it, you're getting full credit, and the learning process happens then, rather than you submitting it and then you look at my solutions later. Okay. Thumbs up. All right. Okay. So, all right, we're going on to the next question. So what I want to do is, can I continue using the document camera? And then, is that all right if I use the
Yeah,
document?
I mean, it's been great. The quality is good.
Okay. Okay. Can you see the problem?
Yep.
Should I zoom in?
No?
That was good. That's good.
Okay. All right. So we are up to Matthew. Is Matthew here? Okay, Maria. So first thing we do is we do the given and the find. So we're looking at a new problem. Let's take a look. We have a block here, B. We have another block A that's on a pulley that's free to go on here, and this is a continuous cable. The words say, a continuous cable is used to support blocks A and B as shown. Block A is supported by a small wheel that's free to roll on the cable. Determine the displacement Y of block A. Determine the displacement Y. I don't see Y on here, but this is Y. Hang on a sec. Sorry, it wasn't, it was cut off. That's Y right here. Determine the displacement Y of block A for equilibrium if the weights of block A and B are 50 and 75 respectively. Okay, so Maria, what's given?
The sketch info, and that A weighs 50 pounds and B weighs 75 pounds.
Great. Okay, Marcine, what do I need to find?
You need to find Y for
Yep.
A.
Yeah, determine the displacement Y. And we don't have to write Y of A. We could just say Y because there's only one Y. And that's it. They're not even asking you for the tension in the cable. Interesting, huh? Right? That's all they're asking for. And this goes back to Angel's question. If they're only asking you to find one thing, do you have to put everything in the table? And the answer is yes. Because you need to know all the things that are known and unknown so you know how many equations you're going to need. I mean, we only have one unknown. We may only need one equation, but odds are some of the equations will have other unknowns in it. So we're up to Mackenzie. Mackenzie,
Yeah.
you're here. Complete the table for me.
Okay, so you have the weight of A, the weight of B.
What about do we know the weight of A and B?
Yes.
Do we know
We
the
also know
direction?
Yes.
So I'm just gonna, again, the given picture is always scrap, and you don't have to write scrap on here. Weight of A, but you know, maybe you should get in a habit of writing scrap, because if you're doing it for someone else that doesn't assume the things are scrap, write scrap on it. Okay, what else? What else, Mackenzie?
So you would still include the tension from A to
Okay,
B?
so let's
Is that
talk
correct?
about the tension now. So, Mackenzie, if this is T here, so let me write 50 pounds and let me write 75 pounds. I always like to write the numbers on the picture so that I remember that I know the numbers, I know the magnitudes. So if this is tension here, if this is T here, and this is the weight, what is T equal to?
The weight.
Right. It's equal to the 75 pounds, right? And why?
Oh, because it's holding it.
Right, it's holding it up. And if we wanted to think about it, we could do a free body diagram of block B, and the weight of B goes down and the T goes up. And if you do some of the forces in the Y, T equals WB, which is 75 pounds. Okay, Luis? Luis, you're here?
Yeah, John.
Okay, great. Luis, I mentioned this in the video, but maybe you didn't watch the video yet. If this tension, if this cable is a continuous cable, it wraps around the pulley and there's no friction, what's the value of this tension in this right here?
Since it's one rope, isn't the tension the same?
Yep, 75 pounds. And then it goes around this pulley. And what is it here?
The same.
75 pounds. Pretty awesome. The whole problem has been simplified because we understand the rule that if you have two rules. One, if a cable's holding the weight, the cable's equal to the weight. We also know now that whenever there's a continuous cable, the same cable throughout, the weights, the load in it is the same.
Joanne, it does change though, right? If it's two different ropes or two different cables.
That's correct. If I had a pin or a ring and there was a cable here and a cable here, this is T1 and this is T2 because they're different cables.
Could you scroll down a little bit?
Yes.
They might be the same still.
They could be the same. That's true. They could be wrapped as a bunch of times around the link, but they can have different values because it's not over something that's a frictionless pulley. So in this particular case, you can't assume that they're the same because it's not a continuous cable. So I'm going to cross this out just so that you know this has nothing to do with this problem. So let's go back to the table. We also have a force of T present, but we know it and we know it because, and if you want, someone asked, I think that was David maybe. I think you said, can we just put T here? Sure. We can put it on the same line.
It has some other
if we want.
directions though, right? Doesn't
That's right. It's all over the place.
The T's
Yeah,
in
that's
the
a
middle
good-
have different directions.
Yeah, that's a good point. Yes, you're right. You can't do it. Okay, I was totally wrong, you guys. Isn't it great when the teacher's wrong? Okay, I was totally wrong. The reason why I was wrong, David, why did you see that I was wrong?
Well, it's the same tension value, the 75 pounds, but it's got 3 different directions.
Okay, good. In fact, it's something even more of a reason. It has the same magnitude, yes, but do we know the direction?
No, because we don't know why.
No, we don't know why. And that was something on your quiz too. And I was really proud. You know, you guys are doing really great. Let me tell you. At the point we are in this semester, looking at your homeworks, but more importantly, your homeworks and your quizzes, you're doing really well. You know, you're doing really well. You're catching things that people may not have caught in previous semesters. So great job.
Joanne?
Yeah.
We know the direction of T on the right,
Yeah.
because it's vertical.
Right.
We just don't know the T's in the middle.
Right.
Is there a reason, like, should it be 3? I guess I'm asking, should it be 3 rows on the table?
You know, maybe, I mean, you guys might say, and most students say that I'm really detailed, but here I'm maybe being a little sloppy, but I'm fine with this.
Okay.
Okay. Because this T, we know, yeah, it's fine. I mean, I guess if we had a problem.
Oh, it's interesting because that's kind of what we're looking for.
Yeah. I mean, in this particular case, it works out that all the T's, the 2 of the T's have the Y. But I don't want to, okay, watch what I could do instead, right? I could call this T, and I already know it. You don't have to write this down, just watch what I do. I could call this T. I'm going to call this T1, and I'm going to call this T2, and I'm going to know this is 75, and I'm going to know this is 75, and then this is why I have a question mark and a question mark. But looking at this, are you going to then say there are 2 unknowns when there's really only 1? I'm a little nervous about that. So that's
what were you
why
gonna
I
do?
put, that's why I only put 1 T with 175 and 1 Y and didn't do this. So I guess you have a choice. You could do whatever you want. Just make sure you have the right number of unknowns in the end. So you could do whatever is clearer for you, a T, a T1, and a T2. But remember that because they're both variables here are the same, there's only 1 unknown. Or you could do what I'm doing, which maybe is a little sloppy, and just putting 1 T and putting a Y here. So you guys choose, okay? All right. I'm up to Liam. So we have 1 unknown, we need 1 equation. So we need 1 body. What body do you want to use to draw a free body diagram of, Liam?
Where the pulley and the cable meet at weight A.
Great. It's a place where they all come together, right? So the free body diagram has WA here. It has, do you want to call it T1? Oh, I'm not going to call it T1 at all. I'm just going to say 75 pounds. And I have 75 pounds here. And I have my Y here. And I have my Y-axis and I have my X-axis. So in the end, I did a free body diagram of, let's just call it point A.
Oh, wait, I think maybe I misunderstood something when I was analyzing that. I didn't realize Y was a force. I thought Y was a distance.
It is a distance. This is a distance here. The force is 75 pounds. The force here is 75 pounds, but the Y component is Y.
She just drew the
Oh, it's the Y-axis. You have the Y-axis going up, and I thought that was a force. Never mind.
Oh, okay. Sorry, I should draw it in a different color. This is the
No,
Y-axis.
my mistake. It's okay.
Okay. So
And scroll
sorry,
up a bit.
they should have not pulled Y. They should have called it H. Right? Should have called it something else. Okay, so now, what about this?
Joanne, scroll up. Thank you.
What about this distance? We're not given angles, we're given a distance, but can we determine what this X distance is? Don't anybody answer yet. And this, we could go back to the problem and see a continuous cable. It's free to roll, block A is free to roll on the cable. Determine the displacement Y. it looks like I don't know what this distance is, and I need to know what this distance is. So we're up to Laura. Laura, could you figure out what that distance is supposed to be?
5 halfway between.
Yeah, 5 feet. Why?
Because with the weight WA, it'll naturally go halfway in between.
That's right. It's free to roll. It's, excuse me, free to roll. It's going to go right to the middle. So this distance right here is 5. So this problem that I chose has 3 features in it. One feature is that the tension's equal to the weight, which we've seen already in other problems. The other feature is that this is a continuous cable, which means the tension's all the same. And the third thing we found is it's free to roll, and we're able to determine what this X distance is going to be. Okay? I'm going to give you a moment just to look at this. Okay? Don't move on yet. Okay, I want to answer a question that I had heard from a student. Can you start using sine? At this point in the course, you could start using sine if you want.
That was me, Joanne. Sorry.
What? What?
The sign question.
Oh, Luis, it's totally fine.
Yeah.
I'm glad. I'm so glad that you guys have a way of communicating with each other, because you're going to learn more from each other than you will from me. And it maybe feels a little sad for me, but that's the way it goes. And it's really important. That's why it's so important for you guys to have this community of students. So I'm so glad you have a way of communicating to help each other, because that's more important. Okay, or equally important. Okay, so sine, you could start using sine now. Reason that we use cosine and we use the direction angles is so that you made sure you got the appropriate negative and positive sign, S-I-G-N, sign. But now you're comfortable, and you use sine before a whole bunch in physics. The only thing you have to remember is if you use sine, you have to remember to put the correct positive or negative sign. Okay, you guys take a look at this problem. If I did components of this force with a y in it 5, this right here would be 5 squared plus y squared, and it would get too complicated, and we're not going to do that. This is the first time you're seeing a problem where I'm actually going to put an angle in, alpha. So typically, this is another thing that we're seeing in this problem. This problem has so many features, and that's why I've chosen it. Normally, if it's a ratio, they give you distances, you use the ratios. If they give you angles, you use the angle. But here, there is an unknown distance, and your math is going to get way too complicated. So instead, I'm going to use alpha. Okay? So how many equations? I'm up to Cody. How many equations did I say I needed?
1.
1. And what equation do you want to do? We only need 1, right? And it's a 2D problem, which means we have 2 equations. Some of the forces in the x equals 0, some of the forces in the y equals 0. Let's just try one. So Cody, which one do you want to do? Considering where the unknown is. Where's the unknown?
Yeah, no, sorry, my screen's kind of small. In the y.
It's in the y. So are you just looking at the page? Cody, do you see everyone right now?
No,
Cody?
I see the paper.
You just see the paper. Okay. Okay. Oh, you're probably okay. All right. So let's do one of the equation, and we're going to use the sum of the forces in the y. And you guys are liking to use sine, so let's try to do that. Let's say we have, and is this alpha 2 here, you guys? Is it alpha? Is it the same on both sides?
Yep.
Should be the same, shouldn't it?
Yep, because it's the same. So I'm making alpha here and alpha here. So what is it? It's going to be 75 times the cosine of alpha minus 75 times the sine of alpha. Notice I had to put the negative in, right? Because I'm using sine. Oh, I'm doing x. Darn it. Sorry. Nobody caught me.
Yes, you think.
Sine of alpha, positive, plus 75 sine of alpha. See how rusty I am in doing sines? Minus 50 equals 0. So that's why am I just, oh, I know what I'm doing.
If you used cosine, would you need to do like some 90 minus alphas? Is that what you would put in there?
We probably wouldn't want to do it. Once you don't want to solve a statics problem if you have these cosine or sine functions like cosine of 90 minus alpha. I mean, unless you remember all those trig functions, I don't.
I mean, they are just like a Google search away.
Yeah, you could search. I would just stick to not having to do that. I would not do ratios if there's a distance that's unknown, and I would not do a cosine or sine if I'm using 90 minus alpha or something like that. Okay, so this is 2 times 75.
Could you raise up the paper?
Oh yeah, thank you.
Thanks.
2 times 75 times sine of alpha is equal to 50. Sine of alpha equals 50 over 2 times 75. That means alpha is the inverse cosine, and alpha turns out to be 19. Could somebody check my work? 19.5 degrees. Somebody else get that?
So when you're
Yeah, I
not
got that.
using
Yeah, okay, great.
the cosine, you don't need, because like normally we need to do the 90 minus alpha because we need the theta y, which is off the y-axis.
Right.
But with this, you're not using that, you're ignoring that.
I'm starting to use sine instead, so it decreases the amount of math work I have to do.
Julian.
Okay. Yeah.
So if we were to actually be using cosines, it would be fine to find the angle from the vertical axis. That would be a good.
Yeah, you could use that axis instead.
Okay.
I mean, this is not the statics part. Do you guys agree this is the math part? Right? It's math. You guys are better at math. You remember all the trig functions. You could do it any way you want. For me, I'm doing it this way because I could get through it really quick.
Angel, I think that's a good idea because it would be the same. It would be theta y. Theta y would be the angle between the vertical axis and each tension.
Yeah, that sounds fine. Could I keep going though?
Absolutely.
Okay, so now we have alpha. So now we're saying the tangent. I'm again doing math. I'm trying to find y. The tangent of alpha is y over 5. And so y turns out to be 1.77 feet. Thanks, Edgar, for checking the math. I mean, you guys are really competent in math and you could solve it any way you want. So is everybody comfortable with the problem? Notice we only needed one equation, right? Had we done had we chose to do the sum of the forces in the X, what would have happened? It would have been 75 cosine of alpha minus 75 cosine of alpha equals 0. Would I have been able to solve it? No. Right? So I think a lot of times what I see students doing is their first equation is sum of the forces in the X. Because you're so used to doing sum of the forces in the X, sum of the forces in the Y, sum of the moments in the Z. Don't think like that. As we go along the semester, we're going to constantly be looking at what equation can we do first to solve the problem the quickest. Because in engineering, time is money.
If we were to want to do the sum of forces in the X, we'd probably want to do a different force body diagram which labels the tension as 50 pounds, right? And the weight at 75 pounds.
Say that again?
If we were to want to do the sum of forces in the X direction to solve this problem, we'd probably want to set up a full body diagram, a different full body diagram on like a different point, like probably at the point above weight B, and label the tension as 50 pounds and the weight is 75 pounds, right?
Well, right now we're doing statics of particles problems, right? If we pick this point right here to do our free body diagram of, the only equation we have is sum of the forces in the Y. Right? And we're always choosing a point where all the forces are, including the unknown.
Yeah, that makes sense.
Right? So we're not doing a free body diagram of the whole thing, because then we would have to do some of the moments, and we're not doing some of the moments yet. So you want to pick the point where all the forces converge.
Sounds good.
Does that make sense, Angel? Like you wouldn't want to do it over here because it wouldn't help you.
Okay.
I mean, if you drew the free body diagram, the whole thing, I mean, do I want to do that?
I was just overcomplicating it. I'm sorry.
If I had the weight here of 75 pounds and I went around the pulley, and I know the tension here is 75 pounds. And then this is my Y distance, and this is my 5. I couldn't do some of the forces in the X. Because this is the only X force, because you're missing the forces in the pin, which we haven't gotten to connections yet.
But I think I was trying to replace that tension with the tension, like the force of the pulley or of the weight A acting on that as like a pulling force, but I don't think that's valuable.
Okay,
I don't
well,
think that's doable.
Well,
Wait, I mean that,
and I'm hoping I'm not confusing everybody, but hang on. Wait, Jason, if I wanted to include this weight A, which is 50 pounds, this is internal. Here's my 75. So if I wanted to draw a free body diagram of this whole thing here, I would have my 50, I would have my 75, I would have my tension, but I still have something missing. There's connections here. I don't want to move on to this. This is just complicating things. Let's just go back to here. Hang on, Jason, you'll have to ask me on the side. So when we're looking at this problem, just concentrate. Right now, we're doing statics of particles problems. We're not doing free body diagrams of huge bodies. We are only doing free body diagrams of points to simplify it. And we're picking points. We'll get complicated in the future, but not yet. We're picking points where all the forces are converging. Okay?
Sounds good.
Okay. So notice in this problem, I didn't find components because we're really only looking at one force, right? But if I wanted to put the components in here, which is our step in between the free body diagram and this, our component of this force would be, you know what it is, it's alpha, so it would be 75 times negative cosine alpha I plus cosine alpha J pounds, and that's this one. And then this T1, this other one is cosine alpha I plus cosine alpha, no.
Yeah, wait a minute. The alphas aren't the angles to the axes.
Right. Sorry, I'm just student using sign, and you can see how I'm getting stumped up, but look at it now. So this force, the y component, this is alpha, so it's cosine of alpha, and I have to remember to put the negative in. And then the y component of it is going to be sine of alpha. And then for this force, the cosine of alpha, it's positive. And then the sine of alpha is the y component. Okay, David, good?
Okay.
Thanks. Okay, let's do another 3D problem. Now we'll do a 3D problem.
We didn't solve that problem. We didn't get the distance y yet.
Yeah, we did.
Yeah, it popped up.
Oh, there's a trig on the side there. I'm sorry. I was doing another calculation. Okay.
Yeah, no, sorry. Okay. All right, we're going to start this problem. We're just going to discuss it, and then we're going to go into breakout rooms and work on it together. So everybody with me? And these problems are also posted on the module too, if you rather look at it that way. Is everybody ready to move on? Thumbs up? Okay. So we have a truck here with the flatbed in the back. We have a weight that's on a chain, and we have 1, 2, 3 bars. Determine the force acting along the axes of each of the 3 struts needed to support the 500 kilogram block. Okay, so let's set up the problem together. Okay, so we are at Jordan. Jordan, okay, what's given?
The weight of the block and the sketch info.
Okay, sketch info. And what's the weight of the block?
500 kilograms.
That is the mass, right?
Right. Okay. So the weight of the block would be
Right.
500 times, or
500 times?
9.8.
Okay. And I'm very glad that you said the weight was equal to 500, because everybody's going to make this mistake once, and let's not ever make it again. Okay? So once you get the mass, and I know I mentioned this before, sometimes people plug in the mass as a weight. So as soon as you're given a mass, calculate what the weight is. It's 500 times G. And it comes out to be
5,000.
Where is my stuff? Do I not have this problem?
Newtons.
Ah, no, I have it. Good. Okay, it comes out to 4905 newtons. Okay, so whenever you're given a mass, convert it right away to weight. Okay, and find, Jordan, what do we need to find?
The force acting along the axis of each of the struts. So we need to find the force of AD, AB, and AC.
Great, great. So now, remember we got this in this discussion on Tuesday that sometimes people are confused, is it AB or is it BA? I don't know how you're feeling about it, but I'd like to just write strut 1, strut 2, and strut 3. And just say this is strut 1, this is strut 2, and this is strut 3. So then you have to worry about, is it going from A to B? Is it going from B to A? Or are you more comfortable just saying A, B, A, C, and AD? Should we stick with AB, AD, and AC?
So AB is going to be compression, but AD and AC are going to be tensions.
Good, we're going to talk about that now. So I'm just going to keep it, and I'm going to keep using the AB, AC, and AD. And the reason why is my solutions is an AB, AC, and AD, and I'm going to photocopy them and post it online on the Canvas site. So I don't want to confuse you with using different variables. Okay, so what are the forces that are present? We'll talk a little bit about compression and tension in a little bit. Jason Lee. Jason Lee.
Yes.
You here? Good.
Yes.
Okay, what forces are present?
The weight.
Good. Do we know it?
Yes.
Do we know the direction?
Yes.
Okay, what else?
And we need to find SAB,
Yeah.
AC, and AD.
Okay, do we know their magnitudes?
We don't.
Do we know the directions?
Yes.
Okay, how many unknowns?
3. And it's going to be 3 equations and 1 body.
And why only one body?
Because it's a 3D problem.
Right, it's a 3D problem and we could get 3 equations, some of the forces in the X, some of the forces in the Y, and some of the forces in the Z.
Right.
Equal to 0. Okay, so now let's take a look at this. So if we have this, oh, what's the force in the chain? Wait, Jason with an E.
I imagine that the force in the chain is the weight of the block.
That's right.
Neglecting the chain's weight.
Great, right. So we don't have to put the chain in here at all. We know it's going to be equal to the weight. It's going to go right through this thing. So if there's a force going down, we know there have to be some forces going up, which means, okay, let's see where we are. Jack.
What? That was my question?
What?
It's too easy.
Oh, okay, Jason, you want to continue?
Okay.
Okay, so if the weight is going down, one of these struts, at least, has to have a force going up. If the force is going up towards point A, is it a tension or compression?
It would be a compression.
Okay, let me repeat that. If the weight is going down, the weight's going down, at least one of these struts here has to be pushing up because it's got to be opposite. If there's a force down, we have to have a force up. If one of these is going, or any of these are going up, it's going to be compression because it's pushing towards point A. Let me say it in another way. Jack, when we draw tension, how do we draw it? Which direction is tension drawn in? Jack, are you here?
Yeah. Away?
Tension is always drawn away. So if I draw AB away, AC away, and AD away, they're all drawn in tension, right? Correct, Jack? If I drew them all away, they would all be drawn in tension. Is that correct?
Yeah.
Yes. Okay. Isaac, is it possible for them all to be in tension in this problem?
No, that would cause an acceleration
Okay, why?
because there's no forces going in the other direction.
Right, because there's no way, if the weight's going down and all these are going down, this thing is just going to collapse. There's got to be something holding it up.
It looks like AB has to be compression.
It could be AB, that's right. Okay, so, but we're gonna check. Now, what I want you to get in a habit from, to do, just like, we're gonna be doing solutions of a truss. Can everybody picture a truss in their mind?
Yeah.
A bridge with a lot of triangles?
Complicated.
Trusses are either in tension or compression.
What can you
And,
define truss a little more? Or just triangle bridge is okay?
Yeah, just let's keep it triangle bridge, okay. Otherwise, I'll talk way too much and you never will. Lots of triangles in a bridge, okay? They take either tension, each of the truss members take tension or compression. So what we do when we do that, and we're not going to do trusses until the last third of the semester, we always draw all the forces away in tension. So if we get a positive value, it represents tension, and if we get a negative, we get compression force. And that's what we did.
Isaac, triangles make up the frame of the truss.
I think I'm mixing up like trusses versus whatever you call suspension cables, which I
Yeah, you
would
guys,
assume can only be
here's a
tension.
truss. You've seen those? Those are trusses.
Oh, okay.
Okay. Okay. Remember here, we drew the tension, we drew the strut going down, remember? We drew it in tension away from C. But in the end, we got a negative value, which said it's going in compression. So even though Isaac thinks AB is probably in compression, we're going to draw them all in tension. So if we get a positive value, it's tension, and if we get a negative value, it's compression. Got it? So on my free body diagram, okay, so we were 3 unknowns, 3 equations, 1 body. Hyoji, we only need to draw a free body diagram of 1 body. What body do you want to draw a free body diagram of? Or what point? Hyoji, maybe he's not here. Gerardo, what point do we want to do a free body diagram of?
The 8 points.
Point A. And point A will have the weight going down, and it'll have these 3 struts. Okay. And now I just want to show you all the math involved in these 3D problems. Because when you do the 3D statics of particles problems, even though there's only 3 of them, it's going to take 7 pages to do. 3 problems are going to take 7 pages. It's long. Maybe you'll get it done in 6. But just look at this. What I'm doing is for each of these struts, I am solving, notice, for each of these struts, it's all given distances, right? So we're going to solve for components using ratios. I'm going to use the ratios to find the unit vectors. And then this represents my first force. And I'm doing checks. A positive, negative visual check. Then I'm going to the next strut, solving for the components. Going to the next strut and solving for components. And then I'm going to plug those values into my 3 equations, and I'm going to get 3 equations, 3 unknowns, and I'm going to set up a matrix, which again, I'm going to show you a video of. So right now, I'm going to put you in breakout rooms, and you have a little more than 20 minutes to work on solving the rest of the problem. We already did the given and find, we did the table, we did the free body diagram, and now we're going to do the solution, which consists of components, and the solution. So I'm going to, does anybody have a question before I put you in breakout rooms?
How will we be able to access the question when we're in the breakout rooms?
It's on It's on the Canvas page.
Okay, I'll find it.
It's written under today's date.
Joanne,
If
I have
we
a
want-
question about that
Yeah.
setup.
David,
If you look back at the picture, at point A, I don't see anything going in the positive Y, right? All of
Correct.
its weight goes, let's see, negative Z, it goes
Right.
down,
right.
but nothing is going in positive Y. So are you, that looks like another example where it's going to be unbalanced. You're going to have a bunch of stuff, I guess pushing
That's
into
why-
point A,
Right.
but what's going to balance that?
Right, so the fact that I did not, that's because I decided to put them all in tension, there's nothing balancing, there's no force going up in the Z direction right now. So what does that mean you're gonna get? What values are you gonna get for these struts? At least one of them is gonna have a what?
A negative?
A negative,
Hmm.
to show that it's actually going up. We could take a guess, and Isaac said he thinks it's this one, but we'll check it out and see.
Oh, I
I'm
see.
trying
They're
to
not all
get
going to
you-
be this. Okay. Okay.
I'm
yeah.
trying to get you into the sign convention of drawing things that you don't know which way they're going, draw them away so that you're drawing them in tension. And then if you get an answer in negative, you know it's compression and it's actually going in the other direction.
Okay. Okay. I got
Okay?
it. So like all three struts, in my head, they were all doing the same thing, but I guess we're gonna find out that maybe they're not all doing the same thing. Okay.
Right, they can't.
Got it.
They can't, because like you said, there's no way for all three of these to be pushing down. Otherwise, this whole thing is going to just slam on the bracket.
Thanks.
Okay? Any other questions before I put you in the breakout room?
Joanne?
Yeah,
So once we finish the question and we want to check our answer, we just go back to you, correct?
yeah. I'm going to have, I'm going to post the solutions, but we'll come back at a little bit before. I'll have you in the breakout room for about 15 minutes and then we could come back. Does that sound okay? We'll regroup.
Yeah, sounds good.
Okay. All right, great. I'm going to put you in there now.
Joanne, I've got one more question.
Yeah.
On our free body diagram for just, I guess 3D problems, do you want them typically done like not in a generalized like 2D form, but you want them in a 3D form?
Yes, you
right?
have to draw them in a 3D form. And I did see a couple of you in homeworks starting to draw or drawing 3D problems in 2D. You could draw them in 2D too to help you visualize it. But in the end, I need a three-dimensional problem, a three-dimensional free body diagram. In engineering, when we deal with 3D problems, we draw three-dimensional free body diagrams. Okay? And sometimes we draw them on CAD, which is most of the time that's what we do. But you could draw them in 2D as well to help you for visualization, but you need to draw them in 3D because you need more practice drawing in 3D. Okay, I'm putting you in the breakout rooms now.
Hi, Joanne.
Hey.
Can I ask?
POG? Okay, hang on a sec.
All right.
Hey there, I just put everybody in breakout rooms.
Oh yeah, I was in a breakout room,
Oh,
but
you were. I'm realizing I should have stopped the, hang on a second. I should stop the recording.
oh.